Along with partial pressures, one of the things you can also use in using the ideal gas equation is you could use what's called mole fractions. And a mole fraction is exactly what it sounds like. It's the moles of one thing over the total number of moles. So you can see the equation here. They use the letter X as the symbol for it. Don't even worry about that, but that is the letter that they use. Okay, but notice it's the moles of the gas in question over the total number of moles. Okay, and the reason that that's important is because you can use that to figure out the partial pressure of a gas. I'll show you here in just a second. Now, one of the things that's interesting about mole fractions is, again, they use the letter X, and you don't actually leave it as a fraction. You don't leave a mole fraction as a fraction. Why do they call it a mole fraction? Again, I think if we could go back in time and change some of these things, it's like, why did you name it that? Okay, so you take the moles of the question of whatever they're asking you about, you put that on the top, you put the total number of moles on the bottom, and then you write your answer in the form of a decimal. And the nice thing is there's no unit, so you don't have to worry about moles or grams or anything like that. Okay, so example number 1 here. It says a mixture of gases contains 12.47 moles of nitrogen, 1.98 moles of hydrogen, and 8.15 moles of ammonia. Calculate the mole fraction of N2. So since they're asking about the mole fraction of N2, that means we put the moles of N2 on the top, and then on the bottom we put the total number of moles. So we take all of these moles here, we add them all together. And then we take 12.47 and we divide by that total number, and we get an answer of 0.552. Okay? And notice, yes, it's written as a decimal. You don't leave it as a fraction. Okay, example number 2 says 2.54 grams of CCl4 and 3.2 grams of argon gas are combined together in a 4.2 liter container. Calculate the mole fraction of argon. Notice in this case, they give you grams in the question though, so you have to convert those grams to moles. So we're going to take 2.54 grams of CCl4. The molar mass of CCl4 is 154 grams in 1 mole. So I'm going to take 2.54, I'm going to divide by 154, and that equals 0.016 moles of CCl4. And then I've got to do the same thing with argon. I'm going to take 3.22 grams of argon. I've got to convert that to moles as well. Argon has a molar mass of 40 grams per mole. So 3.22 divided by 40 equals 0.081 moles of argon. Okay, and what does the 4.2 liter container have to do with this? Nothing. Okay, mole fraction is just the moles of whatever they're asking you about. So they're asking you about argon. So we're going to take the moles of argon, so 0.081, and over the total number of moles, which is 0.081 plus 0.016. Okay, and then make sure you add those numbers together on the bottom before you divide them. So the way I put that in my calculator is I'm going to go 0.081 divided by, and then I'm going to put in parentheses 0.081 plus 0.016. Again, do this on your own calculator. Make sure you get the same answer as me. Okay, and I get a final answer of 0.835. Okay, so again, don't leave a mole fraction as a fraction. Make sure you write it as a decimal. Now, the reason that mole fractions are important is because once you know the mole fraction of a gas, you can use the mole fraction to determine the partial pressure of the gas. So if you, using this equation right here, so if you know the total pressure in the container and you know the mole fraction of the gas, you multiply the total pressure by the mole fraction of the gas, and that gives you the pressure of that gas, the partial pressure we call it, okay? So example 3 says, using the data from example 1 and using a total pressure of 2.35 atmospheres, what is the partial pressure of N2? Remember, partial pressure means just the pressure of the N2, not the rest of the stuff. So from example 1, we saw that the mole fraction of N2 was 0.552. So if we want the pressure of the nitrogen using that mole fraction, the total pressure is 2.35 atmospheres. And we're going to multiply that by our mole fraction, the 0.552. Okay, and when we do that, 2.35 times 0.552, we get the pressure of nitrogen in that container is equal to 1.30 atmospheres. Okay, and that's the last example, but let's look like up here at this one. Okay, let's go back to example 2 here. So here's our mole fraction of, this was argon, right? So that means that of the moles in that container, 0.835 out of 1, right? And the total would be 1, 0.835 of them are argon. So let's say the total pressure was, I don't know, 8.17 atmospheres. Okay, that equals the total pressure. Okay, we can use that mole fraction to determine what the pressure of the argon is. So we would take 8.17, the total pressure, and then just multiply by 0.835. It's almost like we're using percents here, but it is instead of out of 100, it's out of 1. So 8.17 times 0.835 equals 6.82. So the pressure of argon is 6.82, which means we could also use that to figure out the pressure of CCl4. Okay, if we use that same logic, how many moles of CCl4 do we have? We have 0.016. So if we took 0.016 and divided by 0.081 plus 0.016, we would get the mole fraction of the CCl4. So 0.016 divided by 0.081 plus 0.016, close those parentheses, equals 0.165. And notice that 0.165 plus 0.835 equals 1. Okay, so it's almost like we're doing a percent here, but out of 100. Instead of out of 100, we're doing it out of 1. So the mole fraction, the mole fractions of all the different gases will always add up to 1, just like percentages will always add up to 100%. Which means that the pressure of CCl4 is equal to, again, the total pressure, 8.17, times its mole fraction, 0.165. Okay, so 8.17 times 0.165 equals 1.35 atmospheres. Okay, and of course, notice that the pressure of the CCl4 plus the pressure of the argon, so the pressure of CCl4 plus the pressure of the argon equals the total pressure. 6.82 plus 1.35 equals, of course, 8.17. So in a problem like this, the partial pressure of all of the gases, just like how we've seen before when we talked about partial pressures, the partial pressures of all the gases will add up to the total pressure in the container. And so if there's 3 gases, obviously we would need 1 more to get that total pressure. But using the total pressure, this equation right here, and multiplying by the mole fraction is a great, easy way to find the partial pressure of an individual gas in that container.